All right. I wanted to take a look at this body table thing that you found posted inside Moodle and how we can use it to measure areas underneath this standard normal probability graph, which, as we've said, translate to probabilities. So, yeah, sorry, it didn't dawn on me until now. I'm going to fill this in later. I'm not just writing my initials up in the corner of the board because, like, I'm an egotist or something. Anyway, so I've got a copy of this here. Mine is a little more condensed than yours. I apologize. Our textbook is now doing something where the chart is bigger, but that means it takes 2 pages. So I'm sorry. Uh, anyway, so the little picture at the top, I kind of want to draw your attention to, and we'll take a look at it in the context of how to use this for an example or two. So say we wanted to know how likely it was that if we were just to pluck a value out of this standard normally distributed data set, that it ends up falling in between these two values. I know if you think back to your algebra background, you may remember that we usually use x for a variable. We're using z here. I promise it'll make sense eventually. For now, just roll with it. So z is kind of our, that's what we use when talking about the standard normal. Anyway, so we want to know how likely it is that if we pluck a value out of here, it's between 0 and 0.84. So I'll draw that guy in right here, so because it's going to end up looking an awful lot like the picture that's sketched at the top of the handout. We're wanting to measure that area between those two goalposts, the two vertical lines that I've drawn out right there. All right. Now, in terms of how we use this table, I usually describe it, it's almost like a crane game, like you'd see at the front of a store. You're basically going to slide down until you see the first bit of your target number. So 0.8 for me is about right here. And then we're going to move over until we're sitting underneath the last digit of 0.04 in this instance. So I see 0.8, I go over to 0.04 right there, and then in the middle, that's the number that's giving us our area here. So, all right, so that's the idea. So, like I said, you go down, then you go over, okay? All right, let's take a look at another one. So, same principle in effect. Between 0 and we'll do 2.21 in this instance. Okay, so same idea. All I would really need to do here, this is kind of a sketch. It's not accurate. Technically, 2.21 is way out here, right? But just for argument's sake, I'm just going to replace that with 2.21. If you wanted to redo the sketch with it further out, that's totally fine. But again, we're measuring that same kind of area, the same shape that's being imagined in our little body table picture here. So I go down, I look up 2.2. Note that first column does not correspond to 0.01. It's actually zeros at the end of that. So we actually need to hop over that first value and go to the one in the next column where 0.01 is, and that's 0.4864. So those are the probabilities we get just from looking these values up in the table. Okay? Okay. One thing I do want to point out, we may see some homework exercises where instead of talking about probabilities, they'll talk about percentages, like what percent of this data set should live in here. Usual probability routine, we can convert this to a percentage by moving our decimal place over a couple of times. Okay, so there's our first couple of examples down. I encourage you to play around with this some more, just in terms of using the table. But we'll see it work in the context of some more examples in just a sec here. All right, so let's see. Get rid of that 2.21 because he's not what's coming up next. All right, so the next example I want to take a look at, it gets rid of that 0 that was in the back, sort of giving us this cutoff right here. So say we wanted to know the probability that we pick a z-value that's less than 1.26. So I can fill in my 1.26 here, same as I have previously. Okay, so if we want anything, as you say, everything that's less than that, if you have your inequality arranged like so, the point of the less than sign kind of directs you. You want everything off to this side of 1.26. So we're shading this in. I need all of that stuff. Okay. Now, our chart doesn't give us that, so we might end up kind of freezing, like, oh crap, what do I do now? It doesn't give us everything, but it does give us this bit, right? So that part we can look up in the chart. The trick is, what do we do about all this other stuff? And here's where those base properties of the standard normal distribution that we laid out in the previous video end up coming into play. So hopefully, as you recall, the total area underneath this entire graph is, that's right, it's 1. So we have a total area of 1 square unit, whatever that unit happens to be. So we also know from one of our other properties that this graph is symmetric about this bump right here at 0, right? So this vertical line I've got drawn in right here cuts this shape exactly in half. And half of 1 unit of area is 1/2, or 0.5. And that means everything under here, which is conveniently enough where the cutoff starts and the values in our table start kicking in, come into play. So we can kind of break this into 2 pieces. We figure out this area. We don't have to work too hard for that one. This one, we have to look it up in the table. So the probability that z is less than 0 plus the probability that z. And you don't really need to split it up like this. I just like writing it out this way. I'm less visual. I tend not to work with the graph quite so well as having the formulas to work with. But anyway, so this is exactly half of our area. So that's 0.5. If we look up 1.26 in our body table, when I did that, I saw 3962. So I add these 2 guys together. So we have 0.8962, and that's our answer. Okay, so hopefully, that makes sense. If we change this up a bit, let's use, 0.27. So my cutoff point down here changes. Again, I'm really lazy and I try not to mess with my graph too much because I suck at drawing, and I've got a decent looking picture here. So if I change that to 0.27, the same principle holds. My table gives me this piece. That is exactly half. So the only thing I need to change is that guy right there, which means that piece is still, this chunk is still 0.5 because we're still grabbing exactly half of our total area. Right here, if I look up 0.27 in the chart, I got 0.1064. Then when I add those together, I get 0.6064. All right, so we've seen how to use just sort of the base table lookup if we're given 0 up to a particular cutoff point. If we throw away that cutoff point and still have this less than, we've seen how to handle that. I wanted to take a look at a couple more examples where we flip the inequality around to see sort of the difference there. Let me go ahead and get rid of this 0.27. All right, taking a look at my examples here, say z is greater than 1.5. So instead of a less than symbol, we've got a greater than symbol now. Again, the point kind of tells you in this instance we want what's on this side of our threshold point of 1.5. So now, instead of wanting what's right here, we only want what's in what you might call the tail of the graph. Again, if I were to shade this in, it's that strip, that piece right there. And again, the table doesn't give us this rut row Shaggy. I did that wrong. Scooby-Doo never said Shaggy, but you get the idea. But again, using the symmetry and the base properties of this graph, from 0 all the way over has to be 0.5. That's right, because again, the total area is 1. The symmetry means this is exactly half. So this part is what the chart gives us. This part is what we're after. And together they have to add up to that 0.5. So to get what's in this tail section right here, we can just subtract whatever we get out of this from 0.5. So if I were writing it out, it would look like, well, the probability z is greater than 0 minus the probability that z is between 0 and 1.5. Because, again, these two added together have to give us that guy right there. And if we look up 1.5 now, again, as a note, if you only have this one decimal place, you can sort of mentally fill in a 0 right there. So we actually need that first column this time. If we look up 0.5, 1.50, I saw 0.4332. And when I do the subtraction there, if I'm doing my arithmetic right, that gives me 0.0668. So about a little more than a 6.5% chance that's what ends up happening. So that's that's kind of the idea here. So these two pieces have to add together. This is our table value. So if we subtract that from 1/2, we get what we need. All right, let's take a look at one more before we call it video. I erased more than I needed to. Let's change that guy to, I don't know, 2.07. I don't think I've used 7 on anything yet. So actually I did. We'll go with it. All right, so again, I can cut off that guy. It's 2.07. Again, if you wanted to move this for a more accurate picture, that's okay. Our chart gives us this number. We're actually after this because we want to be bigger than 2.07. So again, these two guys together have to add to 0.5. So that means I can take away from that area of 1/2 the 2.07 value. If I look up 2.07 in my body table, I have 2.0. I go over to 7.07 off to the right. I got 4808 when I look that up. Triple check. Yes. All right. So then when I do the subtraction, that gives me what? 0102, I believe. So no, it should be 0.0192. There we go. I was looking at it like, yeah, I don't think that's going to add up. So now if I add 192 to this, yeah, that should be good. Okay. So you'll notice in the PowerPoint slides for this section, I've kind of combined this into sort of like a 3-part bullet point thing of how we can use the body table to evaluate the 3 things we've talked about so far. So in the next video, we're going to play around with this in a couple of different ways. So keep on watching.